everyone. Welcome to another episode of the Bamboo U podcast. Today's guest is Neil Thomas.
Hello.
Hi, Neil. How are you doing today?
Yeah, good. Thank you.
We are really lucky because we have him with us here in Bali during Bamboo U. And Neil is the director and founder of Atelier 1, and he has done some exceptional work and has designed and engineered all kinds of incredible, not just lightweight structures, but also stage sets and incredible pieces of art. And the first time I met Neil, I actually didn't know who he was yet. I met him at the Green School, and he was sitting in the Peace Garden, and I had no idea what it would lead to. But now I think we're 5 years in, right, Neil?
Yeah.
5 years in, and Neil has designed some of the most interesting things with us made out of bamboo, and has really taken bamboo to a whole nother level by applying important engineering work. So, Neil, I guess my first question to you is, what got you so inspired about bamboo? And, you know, you've done so many incredible things already with other materials in really unconventional contexts. What got you into bamboo specifically?
Hello, Oren. Yeah, it's great to be here, actually. Thank you. As you said, I've run Atelier 1 now for over 30 years, structural engineers. I have a partner, Aaron Chadwick, that I share the practice with and have for most of that period. About 13 or 14 years ago, I was working with an architect in the UK called Mark Fisher, who was the designer of stage sets. You mentioned that we've worked on stage sets in the past with bands like Pink Floyd, the Rolling Stones, U2, and more recently Coldplay, Beyonce. And 13 odd years ago, Mark announced that he was actually he had prostate cancer. Mm. And that he didn't have a great deal of time to live. And he sent me an email, and this email said, I would have liked that we got drunk together a few more times. And it also said, go and find John Hardy. And I had no reason to be in Bali apart from Mark's request. But because it was Mark, who had been very close to, and he died shortly before I finally actually visited, and I came to visit John Hardy. I spent 3 or 4 days with John in Bali, and I saw something that entirely changed my life, actually. Not changed it, completely changed my life, which was bamboo. I mean, I discovered bamboo here. I mean, I think all of us probably are aware of bamboo as a kind of material. You know, you see it in gardens, picket fences, and sort of, you know, that sort of thing. But what I saw when I came to Bali was something completely different. It was buildings built from bamboo, structural bamboo. And quite honestly, it was a revelation. And what I found was, after having been an engineer for nigh on 30 years at that point, maybe 25 years, that I walked here, I came into and found a new material. I mean, that's just remarkable. A totally new engineering material. And I came home from that visit with John for a few days, where he'd taken me around, you know, the Green School and some of the houses that had been built and designed by him, his daughter Elora, who has a practice here. I went back to the UK, and I told my colleagues, particularly my partner Aaron, that we were going to be engineering bamboo, and they thought it was a joke. And 13 years later, 3 months ago, we were awarded the Institution of Structural Engineers Award for Sustainability. As they said, it was the most unbelievable, the most incredibly sustainable building they'd ever seen. And it went on to win the same awards, the Supreme Award for Engineering, which is the building. So they award a series of awards, 10, 11, 12 awards, and then they choose from those 10 or 11, 12 this Supreme Award. And it won the Supreme Award for a bamboo building, which was the engineering for the Green School Gymnasium. So
the Green School Arc.
Sorry, yeah,
the
Green School
which
Arc.
is the gymnasium.
Yeah.
And so what do you think it was? I think it's, you know, you've said this to me before, but it's interesting for me to hear, because, you know, in Bali, we're building with bamboo. Sometimes it's a bit of fishbowl, right? You don't necessarily know what it's like on the other side, and you live a lot of your time in the other side because you have a engineering practice that works with lots of different materials. And you've said this before, where when you came back after your initial visit and said you wanted to work with bamboo, everybody kind of laughed, but now they're not laughing anymore. And what is it? What do you think's changed? And what do you think led to the arc being something that was considered for these important awards?
So I think that bamboo structures, the things that I discovered, I told you when I arrived here, bamboo structure existed within a kind of bubble. And it was a bubble within the tropics, and it's the tropics across the kind of, all through the equator, as you go from the east, Indonesia, Bali, and across Central Africa through South America. So it existed, bamboo structures. But beyond that, it didn't really, people weren't aware. And I think what's happened and it has, as I said, been over the period of 12 or 13 years, that more and more people have become more aware of it and its possibilities. And I think particularly more recently, as the world, so very, very and quite rightly concerned about climate change, that actually the looking into the idea of constructing buildings with natural materials is becoming more and more necessary if we are to reduce the carbon emissions from building the construction industry, because the construction industry is between 35 and 40% of all carbon greenhouse gas emissions on the planet. Mm-hmm, yeah. So with the kind of nature of the bamboo itself as a material in its natural form, but also what's happened during that period is this investigation into the idea of taking bamboo from its natural forms and converting it into engineered form. And just to explain that a little bit perhaps, so bamboo grows as a kind of a culm, a little like first of all, bamboo is a grass, not wood like a tree. Mm-hmm. It's different. Trees grow up and outwards. So as you can see that in the when you cut through a tree, you can see the circumferential rings that everybody knows and tells you roughly the age of the tree. Yeah, it grows
out radially.
Yeah. So it grows not only vertically but radially. But bamboo grows up as a tube, and it grows roughly from its overall size and straight up. Mm-hmm. It grows very quickly, and upwards of you can grow to 20 meters tall in a year, and then after 2 to 3 years, perhaps 3 to 4 years, it matures through that period, and then you harvest it and you can use it as structural bamboo. And a lot of the work that's done here and that I experienced in the first part of this period of coming to the Far East and involvement in these projects was structure built from natural bamboo. But what you can also do, which you can do with timber too, is to take those culms, cut them up into smaller pieces or strips or sections of the bamboo by splitting it down into small rectangular sections, putting them back together again with adhesives, and you can form normalized, the phrase we use as engineers, normalized sections, which is like a rectangular section of a beam that you would see in any normal construction, but instead of it being from wood, it's from bamboo. And that now opens up the possibility of introducing bamboo as a structural material into the kind of construction industry that before I discovered bamboo, that is the world that I know and the majority of the kind of Western construction industry is used to. Mm-hmm. So, and I think in terms of, it's always a question that's always asked of me is, how do we apply natural bamboo forms to Western construction? Well, there are certain uses. They can be, for pavilions, canopies, stuff like that. But I think in terms of the general construction, like residential buildings, office buildings, if it's going to happen at all, it will be using bamboo in its engineered form.
Yeah, it's we talk about this a lot, and I did another episode where we talked about bamboo as a round pole and also as a laminate or as a square element, and so I'm curious about that from the engineering perspective. Because the things that you have done with us have been very much focused on round pole bamboo. And so I want to talk about that and some of the challenges with that and what what's really understood and what isn't understood yet, because I think one of the bottlenecks, as somebody who's active in the bamboo industry, is just finding competent engineers who are able to engineer things properly. And so we ensure that as we're doing more and more round pole construction, those buildings are safe and also reputable, right? So we don't want to end up in a situation where everybody's building bamboo buildings, but some of them are falling over or leaning over or just not doing well. So I'm curious about that, but I'm wondering from your point of view, because you've also worked with wood, and wood is also a natural material, right? That has its own characteristics. But what do you think like the limitations and the potentials are for the two different ones? And maybe we start with the laminated bamboo, because that fits into the mass timber movement that's happening, where more and more people are wanting to build buildings using carbon-based materials, which is aka wood and bamboo. Mm-hmm. And how do you think, if you were, how do you think that those two things are going to move forward in the world, particularly in places where bamboo doesn't grow, Europe, England, places like that, versus the other side of the coin, which is what we're doing, which is very unconventional in the overall building practice, but we're using bamboo in its natural form that has its own strengths and limitations. So I'm just curious if you could walk us through what you believe the main opportunities are for those two, because in my mind it's kind of like a branch, right? It's there's kind of the bamboo movement is advancing in kind of two directions that are semi-parallel but also very different, right? Because there's the camp that says, yes, we should take bamboo and turn it into a square and laminate it back together and make it basically a substitute for CLT or glulam. And then there's the other camp that's like, no, bamboo should be a round pole. It's already super efficient, an incredible natural material, and we should figure out how to build bigger buildings that are with round pole construction, which the Arc is basically a round pole, primarily round pole construction and semi-processed bamboo, right? Yeah. So I'm just curious, where do you see those possibilities going, and what do you think? How should people kind of think about that if they're considering either a laminated bamboo as an alternative to maybe wood versus using a round pole?
Okay, probably it's worth just describing, as I understand, where bamboo sits in the kind of world that we, the construction world. And but it's very important to understand that actually bamboo is a natural material, a grown material. So, and when we have been working with bamboo in Bali and with Elora, with yourselves at Bamboo U, you have to understand the kind of nature of it as a material, as a growing material, which is very different to working with materials like steel and concrete, where the properties are known and defined. So steelwork, for instance, is known as an isotropic material because the properties are the same in all directions. Concrete, the properties are very well known, because it's been tested and the codes of practice have been developed over a long time. And timber, although natural, when we generally take timber and work in the construction industry, is you take timber in its form as a trunk and chop it up into rectangular sections that we call normalized sections or
we've
standard.
Made it same as bamboo. We made a square element.
Exactly. And the point about it is that we're able, or over years, because timber's been used for such a long time, that there's a huge amount of testing been done on timber, which allows us to be able to grade the timber in certain ways, so we can predict exactly what each of these individual sections of the materials, be it oak, beech, or other material, we know roughly how they're going to work. So we're able to specify it from a code of practice. When I mentioned earlier on, or we were talking earlier on about the fact that bamboo, for me, is a brand new material. In 12, 13 years ago when I first discovered it, the codes of practice that have existed for years for materials like timber and for steel, concrete, don't exist. So we're kind of starting out at the beginning. And to do that, to be able to use it and build within the kind of rules and regulations that we have, and those, let's be clear, the rules and regulations that we do have are there for safety. basically. As an engineer, your job is to keep people safe. So if there are no guidelines or rules, which there were very few when we first began looking at it for bamboo, then you're kind of having to make those rules up as you go along, which in a way has been fantastic because it's allowed us to build and investigate stuff here in Bali and other parts of the world, which you would never be able to do because we're kind of creating those. We're actually in the process of creating those rules and putting the rules together, the understanding of bamboo. But bamboo is very different from timber, and so one of the things we at Atelier One are very we take extremely seriously is when we take on a material, we know it, we learn to know it and understand it. And when I first came here, it was more than 3 years before we actually started even considering engineering the material, because it's such a complex material and such a remarkable one, and the properties it has, and it's quite difficult to explain some of those things without you kind of seeing what the bamboo is, but it has incredible properties. It's very, very strong in tension, very, very strong in compression, quite weak in shear. But interestingly, rather than that be a kind of issue, you need when you understand the nature of those properties, you work with those properties and you design accordingly. So people have built with bamboo in its natural form for thousands of years, but those natural forms, the culms, it's difficult to integrate those into a lot of architecture in the Western world, into European, North American, the big major cities, because construction, the industry and the kind of types of building we're doing are based upon and work around the nature of normalized sections. We live and work in rectangular boxes, and the sections you go to build up those buildings are rectangular or square. Integrating bamboo in its natural form is quite difficult in those. It's appropriate for certain types of buildings, such as the Green School Arc, the gymnasium, which is a kind of free-form enclosure. So if you're looking at those free-form enclosures in different parts of the world, then yeah, it's absolutely appropriate. And in fact, it's beginning to come through now. People are beginning to ask whether they can do these things in bamboo. In terms of integrating it into the construction industry as we know it, the engineered form of it is far more appropriate, because it combines bamboo in its natural form, the kind of irregular circular form, and puts it back together in a normalized rectangular form. So you can integrate it into the construction industry. But there's something I want to correct you on, which is bamboo is not, or no, never will be a replacement for timber. They are different. So when you talk about steel, concrete, timber, bamboo, they're 4 different things. Bamboo is not a replacement, and there are good reasons for that, because they have completely different properties and they work in different ways.
Yeah. Okay. So
they are complementary materials.
Yeah. No, I understand. So I want to talk a little bit about round pole construction and where we think that will go next. But before we do that, let's dive into looking at, so on a materials level, how do you see bamboo adding something meaningful to the overall mass timber movement and the kind of, I want to call it, I guess it's kind of like a dream. You hear people talking about wooden skyscrapers and building multi-story city buildings using wood so that it's lighter and much lighter footprint as well. Sequestering carbon dioxide, getting carbon credits for buildings that are, because they're made out of carbon-based materials, primarily wood. How is bamboo, if it's different from wood from an engineering point of view, how is it different, and what is the opportunity there that might be, that wood doesn't necessarily have?
From a point of view of, it's very important to understand, because both wood and bamboo will have a huge impact on the carbon footprint of construction.
Yeah.
And let's remember, the construction industry currently produces 30 to 40% of greenhouse gases, which go towards the kind of the heating up of the climate change, the heating up and changing of the planet. And bamboo is currently hardly used in the construction industry at all. It's as I explained earlier, it's a relatively new and young material that people have discovered. And recently something happened in North America. a building in Washington, D.C., built in mass timber, was permitted the use of sequestered carbon in the embodied carbon calculation for a building. So well, you need to understand the difference between, or what the carbon kind of elements of a building are. And so when you consider a building, there are two elements to it. Embodied carbon, which is the carbon dioxide that goes into producing the building itself, constructing it, with the materials where it comes from and all those elements. But also what that building that's been approved in Washington does is allow you to consider the carbon that's gone into the growing of the timber. And again, you have to understand the process. Wood grows, and as a tree grows, it takes carbon dioxide, uses it for photosynthesis, and produces oxygen, and breaks the carbon dioxide down and stores the carbon in the wood.
Mm-hmm. Yeah, so it's a carbon sink. Basically, yeah.
Which is fantastic, because the quantity of carbon dioxide being taken up into it in the embodied carbon is big. So when you do the calculation for embodied carbon in a building, it's usually positive, because you use this amount to produce a piece of steel, this amount, and it's that we're talking about. Wood sequesters the carbon, so you can do the two calculations. You find if you take wood and the other carbon dioxide that you're producing in the process, the sequestered carbon takes it into negative carbon. So where we're talking about achieving zero carbon buildings, what this building in Washington does is show you that you can build buildings using natural materials, which will be not only zero, but negative carbon.
Carbon negative.
Now, where does bamboo come into this? So how long does it take a tree to grow? A tree takes
years.
Well, okay, let's say 50 years even, but
15 is probably the most.
I think if you do it for forestation, you can do it in 20 years. You can build grow a mature tree in 20 years.
Yeah.
So 20 years to get a tree, and then you chop the tree, and the trunk, the bit that's left, dies. So that's it.
Yeah.
So you've waited 20 years for this tree, and then you've sequestered that amount of carbon. Bamboo, amongst its other remarkable properties, grows incredibly quickly. Yeah. And the type of bamboo that we're talking about grows in clumps. So you have a whole series of bamboo culms that grow from a clump, and they grow quickly. As I said, they grow with around a year, potentially the sort of bamboos we're talking about using here, Dendrocalamus asper. They grow over a year, they mature.
After, 4 years you're harvesting.
4 years to harvest, chop them off. But the great thing is they don't die. They grow again.
Yeah.
And they grow again and again. They grow 4 or 5 times. So we're effectively sequestering the carbon, but over a much, much shorter period of time that a tree would be sequestering.
Yeah.
And because of that calculation that's now been allowed through the insurance companies in the United States of America, bamboo now joins that whole potential for sequestering of carbon. And so now that the industry, in its naivety and its youth, is, people are beginning to turn to bamboo and say, well, actually, we can build buildings from bamboo. Mm-hmm. Be it natural buildings, the buildings we're talking about, which are the free-form structures, but perhaps potentially with greater potential in terms of its impact on the construction industry in its engineered form. I think more and more people will be doing that, turning to bamboo. And we're currently working with the University of British Columbia in Vancouver, where we are sponsoring a research project into looking at building a facility to build engineered bamboo, or to manufacture engineered bamboo in north of Vancouver in a place called Hope. Mm-hmm. And so if they're starting to do that in a place in Vancouver where and it's really interesting. They
have lots of trees.
Well, that's really interesting you say that, because the government have just restricted the amount of felling of trees because they've cut so many trees down in northern Canada. Actually, the regrowing, the reforesting is catching up, because remember, trees take 20 years to grow.
So they're cutting more than they can plant.
Yes.
Yeah.
So the alternative, and I'm not saying you bamboo will grow in Canada. I've seen it there. So but I mean, it gets very cold in the winter. So obviously, I mean, so
well, they call they call the tip of Vancouver Island, the Canadian tropics. So.
Well, it grows there, but
warm as
but the point about it is but nonetheless, the kind of question of it grows all the way through the tropics, and so there's enormous 1,600 species of bamboo in the world, enormous number of species. I mean, we've only begun to understand the properties of a small group of those, and in terms of using them. And then there are some bamboos that are better than others in terms of structural use, like from the Far East, Indonesia, Dendrocamas asper, and from the other direction from South America, Guadua.
Yeah.
But again, as it becomes better known and better understood, there'll be more species. We'll have particular uses for particular things, and it's only going to expand that industry, I think.
And what are, before we jump into looking at the other side of the coin, what are some of the bottlenecks or barriers to more people in the wider construction industry in places even as far as Canada actually adopting that? Is it just a matter that they don't have it and there wasn't much incentive because they could just use wood? Or are there issues on a mechanical or on a safety level?
The reason that
if climate change is such a big issue, like why isn't it just like exploding?
So, as I explained earlier, bamboo is a relatively young material in terms of global knowledge of it. Yeah. And as it becomes more and more known, I think it is very likely to expand very quickly into the construction industry. And we are being asked as structural engineers more and more to get involved in projects. And people are saying, well, okay, we're really interested in looking at wood, natural materials, because of the whole kind of climate change question. But people are saying, and can we consider the possibility of bamboo? We've heard that. I hear that question more and more often now.
Yeah.
And I know when we first started doing it, I know David Trujillo, who is a academic at Coventry University, and was sat on the committee that wrote what now exists, the current ISO standards for bamboo, which are still limited. They are not as anywhere near as comprehensive as the codes of practice for other materials. He said we were the only engineering practice who was taking bamboo seriously as a structural material. But that was 10 years ago. But again, it's becoming more and more used. So one of the biggest engineering practices of mass timber buildings in the USA, a company called Fastenep, who are based in New York and Vancouver. We are tying up with them to investigate the idea of use of bamboo. And we've recently been approached about a large project in Italy where we've been asked if we will investigate not only wood, but bamboo as a possibility for a construction material for this development, which is a big 1 million square meter development, which is huge.
And so how are they, at this stage, how are they looking at what elements are the most attractive elements to make out of bamboo, as opposed to, let's say, wood?
Well, interestingly, so I mentioned earlier on, one of the things that we always endeavor to do when we work with any material is to understand very carefully how it works and its properties and what it's capable of. And bamboo is compared with timber, for instance, potentially has much higher capacity in tension and compression. So it's able to carry more load, but relatively low in shear. So the three forces that you need to combine to work. But what they lead you to is that bamboo is not such a good thing for small span things like housing. When you get onto office buildings or large span structures, it becomes much more, has much more potential than I think wood has, because of its ability to be able to carry load. Its tensile and compression capacities are far closer approaching steel than they are wood. But there's an interesting point I'd like to raise there. Often people describe bamboo as the vegetable steel.
Or being as strong as steel.
Yeah, it's not as strong as steel, and it's different in its nature. You have to put together the various properties and understand how they work. So you can't... It's a very big and kind of, I think, a generalization that shouldn't be used. If I was generalizing about it, I would suggest it's probably more like a vegetable carbon fiber, for instance, because steelwork is isotropic, whereas carbon fiber as a material where you lay up into forming structures. You put the fibers where you need the strengths, which is done in racing cars, for instance. So they build the bodies, the storage spaces on aircraft, they're built from carbon fiber because they're massively strong in the explosion. So
And light.
and very, very light.
Yeah, and that's really interesting. That you're basically saying that it actually has a more of an application in larger buildings because it's stronger than wood. But you mentioned, and I want to maybe talk about this because with shear, if you're building with a round pole construction, the shear weakness is really obvious as soon as we drill a hole into it. It splits really easily, and so that action is really obvious as soon as you start working with it. But is it compensated for in any level by turning it into a laminate or an engineered product? Like, are they able to? Have you found that there's ways to reduce it? Do we know whether that can kind of be addressed, or is it still much weaker than wood, even in a laminate in a square form?
So bamboo has very high tensile capacity, very high compressive capacity, and low shear capacity. So when you work with it, you have to understand those parameters and work with those parameters. So if you take a cross-laminated timber, for instance, and it's in the term and the cross-laminated. So what you do is you create a series of layers of timber, and each of those layers, maybe you have 5 or 6 in a section of a beam. One of them is running along the length of the beam, and the next layer down is 90 degrees to it, crosses the other direction. And then it's long along the length, then the next one crosses. So 90-degree layers to each other. What you're doing is so what you're doing there is you are removing the unidirectionality of the shear, and then you can take higher capacity because of the crossing of the laminates. So there are ways of understanding how to mitigate for, or in fact change the shear capacities of the sections in when you take a natural material and convert it into an engineered one. And that's the kind of the challenges or the opportunities, I suppose, is probably more the right expression to use, because once you're able to change the weaker properties and elevate the weaker properties by changing the kind of orientation of the materials as they're joined together, then that means suddenly the what your limitations are change. And if you can elevate those limitations, then you could start to use the real true capacities of the bamboo, which are, as I said, in tension compression, well beyond the capacities of timber.
So there are ways to mitigate
Absolutely.
it. Yeah, that's pretty impressive.
And I think we're very, again, I mean, because again, we're fairly early in the development of ideas with bamboo. I'm sure there will be all sorts of other ways that will be invented to find ways of enhancing the shear capacity of the bamboo to enable to bring the high tensile capacity and high compressive capacity to be able to use those rather than be limited entirely by the shear. And then an example of that, and we are starting to pursue as a possibility, is the methods of Japanese joinery, for instance. So if you imagine in the 21st century, so you take the tensile capacity of a material, its compressive capacity and shear capacity, when you put a beam, how it connects into and is supported by whatever those conditions are, you have to transfer all those forces. So if you could optimize those forces by use of the form of the joint, suddenly, and this is thinking about the way Japanese joinery is done, we could form three-dimensional sections within the connections so that we're taking the best advantage or the greatest advantage of each of those properties. So that's a kind of interesting area of work alone, but one that we've started to think about. But I think
it's a good segue to my next question, which is I really want to, that's engineered bamboo. I think it's pretty clear that it has a bright future in many ways. But what about the round pole? Because I mean, if you look at the Arc, is a really good example. Incredible building. That we were really only able to do because your firm Atelier 1 was involved in making sure that we could engineer it properly, and most engineers wouldn't necessarily even know how to start to do that. And so that's all round poles, and it's bent round poles where we have a whole series of arches, and those arches are basically kind of a proto-composite of round round poles, right, where they're stacked
Yeah.
together to
Yeah,
make and so we kind of manufactured the rigidity, but bamboo's bad in shear, which means that joinery is a big issue, and I know that's something that you've been looking at, how to join bamboo, but where do you see now that having the Arc be this building that got all these awards, like, do you think that's the limit of round pole construction, or do you think we can push it further, and do you think it's possible to do even larger buildings using bamboo in its natural form, as a round pole?
So going back to the Green School Arc, the gymnasium building that we developed with Elora Hardy and Ibuku, Jorg Stam, PT Bamboo, and ourselves, Atelier One. And there's an interesting there already, which is the collaboration and the kind of, which I think is very important to us as a practice, that actually when you work on projects, and particularly with these kinds of materials, you work with people who know, experts in their own field. So Elora and Ibuku as designers, PT Bamboo Pure as builders, and one of the very, very important things in working with bamboo in its natural form is you work with people who know how to work with bamboo. You cannot do it with novices. It just won't work. It's got to be done with people who have experience and understanding of how to carve and form bamboo. And then Jorg, who has the kind of breadth of all those disciplines, I think, and the engineering. So he's a craftsman, he's a designer, he's a builder, and he's an engineer. And so he has all those abilities. So it was a great team. And what we were able to do is to combine a whole series of things that we were starting to talk about doing, which is taking bamboo in its natural form and combine it in a way where you use geometric form or geometric stiffness. So you create surfaces, different surfaces, which nature does readily and has been doing for millions of years in terms of shell structures and folded plates in nature. You'll see them around. But so we were considering combining a series of arches. And what the Green School Arc turned out to be was very much like the body of a body, human body.
Like a series of ribs.
Like a series of ribs, like a chest. Yeah. And so it had a series of ribs which were connected by tissue, muscle, and skin, and they were combined together. So that structure is one completely integrated structure of a series of ribs, the arches, and a series of surfaces, which are doubly curved surfaces, which provide stiffness in the shape of them. And they're made from splits, the kind of when you take a bamboo culm and break it down into pieces, then recombine it as a mesh, and then layers of bamboo unfolded, just flat, to form a kind of skin over the top of that, and that combines together to form a complete structure. Now, what was interesting about it is to form the curves, we had to cut the bamboo and then break it and then reconnect it together. So we added in reinforcement and created these to be able to bend it. So we cut them and then folded it. So you form kind of polygonal arch.
But that weakens the bamboo.
And it weakens, but so we have to reintroduce that stiffness back in. We did so by adding in a series of strips, which are screwed and glued along the kind of arches, and then creating a bundle of arches, or group of arches, which act together to form some level of composite arch form. What was interesting for us about that is nobody had done this before. So, and there were no codes of practices, no codes which we could take guidance from.
Anybody who had done it definitely didn't engineer it.
Well, the people had built larger scale structures, or large scale structures, but not on the scale of this, and certainly not with the ambition and the kind of level of technical I think integration that we were proposing with this building. So what it necessitated is we tested everything, which I think was a kind of shock to everyone. I think not the fact that we had to test things, but the kind of quantity of testing that needed to be done. Yeah. Because we were using techniques of combining things that had not been done before. So that's in the shell surfaces themselves, and the arches being cut and then reinforced, and then the arches combined together to form composite surfaces. All of these things were unknown to us.
And just so listeners understand, when you say testing, you literally mean building parts of the building and hanging load from those parts.
So at a simple level, the testing starts at take one column and hang load in it until it breaks, and it tells you what that column is worth in terms of its load capacity. And then if we're forming a series of columns together to form a bundle, you put a bundle together and load those and bend those and test and break those and find out what it's worth. And then as arches, we have to curve them and then test the arches, and then combined. And this is the really quite fantastic thing about it, is the ambition was met by the response from everyone involved, and that included all the people I've talked about, but the school as well, in terms of providing sufficient funding to allow those tests to be done, and to the point where we actually tested a full-size shell surface
prototype.
Full-size prototype, which you know, because there was no other way of proving it, that's the only way it could be done. But nonetheless, it doesn't alter the fact that it was unbelievable that it happened. But it enabled us to play with the bamboo and understand very, very precisely its kind of properties. But even so, it was still limited. We couldn't test. The more and more testing you do, the better understanding you get of the material, because working with engineering, particularly natural materials, is an issue of probability. Because materials, you can only know the exact performance of them within certain limitations. And so there's a level of probability. So the more testing you do, the more accurate that probability becomes. Something we as engineers have to deal with all the time, the issue. I mean, how does the wind blow? You don't really know. You kind of approximate. So you kind of have an idea, but the wind blows.
It comes from that direction, but does it? Yeah.
Yeah, but if there's a truck going by at the minute the wind is blowing, the wind will hit the building in a different way. So you cannot possibly analyze for all the infinite conditions. So we design for a level of probability.
Yeah, and that's an interesting point, because I'm not an engineer, but my limited understanding from seeing engineers talk about their models, right? Basically, a lot of the time you're making these computer models, and especially with bamboo, because there's so many variables, it's really hard to get those models to be accurate without actually going outside and literally hanging weights from a smaller version or a similar version or a component of the building. To then make sure that your model is actually in line with what the reality of the situation is showing us on site. And so I'm curious, like, was there anything from that process that really surprised you, or did you learn anything about bamboo from the process of engineering the Ark that wasn't unexpected?
I have mentioned that actually we, as a practice, when we get involved with a different material, we kind of need to understand it. And with bamboo, because it's natural in its form, that exercise took a great deal longer than previously. I think the point is, if we kind of got introduced to a new material, there was sufficient information, supporting information, testing, technical data, etc., that we could draw on that. But with bamboo, there wasn't very much to draw on. So we were kind of starting from scratch, and so when everybody got involved, and it's probably worth just a very basic description of how the structure of bamboo works, because bamboo grows as a tube, a column, but as it grows, it also produces these diaphragms. So if you look at a column of bamboo, it is a kind of long pole, and these discrete diaphragms or plates occur up the column, which provide a linkage to the circular form, and those diaphragms occur at roughly equal centres up the pole.
Yeah.
And interestingly, as an engineering aid, they will provide resistance to buckling of the bamboo, which is quite fantastic. But what happens within the structure of the bamboo within the section of the bamboo itself is there are fibres that run up and down the bamboo, which give it its strength. But as it crosses over the diaphragm, those fibres go from being straight, which are very predictable. Well, even given the limited amount of knowledge that was available, they're still relatively well predictable. As it crosses over the diaphragms, they go into
like a bird's nest. Yeah.
Like a bird's nest.
Yeah.
And so they become completely unpredictable. And so we have a kind of basic understanding, and we make certain assumptions about these things, about the properties. But we're currently working with a university in London, University of Central London, UCL, where they are digitizing the form finite element modeling the form of a bamboo column, which will account for the straightness of the fibers in the internode, or the bit between the diaphragms or the nodes, and will account for the higgledy-piggledy nature of those fibers as they cross over the diaphragm. So we will actually be able to account for the relative stiffnesses, which is what this jumble will do. It changes the nature. Because you can imagine a straight fiber, if you pull a straight fiber, it's very strong. If you pull a very kind of a mass of fibers in a higgledy-piggledy way, they are, who knows what they do. So bamboo is a very, very difficult material complex material to understand, but one that we will become more and more understood as time goes on, and more people become involved in it, and it's investigated.
So you think that eventually the models and the information will be there to a much higher degree, where it'll be much easier to estimate the actual strength.
Well, if bamboo goes
in a round pole,
if bamboo in its round form goes the way I believe it will, I mean, I think you mentioned earlier on that bamboo, there are two directions for bamboo: one the round form, and one the engineered form. Both of those directions will expand in the world. You will see more and more of both bamboo in its natural form and bamboo as an engineered form, and so. There will be, yes, as people become more aware of it and more investigation is done, and it's becoming more and more apparent. I mean, we work with universities in Hong Kong, United States, Australia. There's a lot of work being done in Australia on fire performance of bamboo, the mechanical properties in the USA, that's at UCLA, and Kent Harries in Pittsburgh. There are various universities around the world doing different parts of the investigation. You put all those parts together and you begin to get a very good understanding. That's what leads you to allow to create a code of practice. But at the moment, currently, it's interesting. So if we work with timber, you might be working with factors of safety of timber of 2 to 2.5, whereas bamboo currently stands at 5 to 6. Because it's not so well understood. And so because it's not so well understood, you have to allow a greater factor of safety until it becomes better understood, and then you'll be able to reduce that factor down.
And so just so listeners also understand, a factor of safety is you figure out how strong it is, and then you add extra on top of that, right? Is that correct?
I think engineers are known for their conservative nature, but it's not really conservative. It's making everyone you and I know, all my loved ones, my family, safe. You don't design a building to the point at which its capacity is the load it can be applied. You design it for a load above that, so that if it were to achieve the maximum load that you design for, you have a factor of safety over and above, which means everyone stays safe. It's very important. It's not conservative, it's being safe.
Yeah, so
it's very important to me.
On that note, it's easy to say that, I think, but a lot of these buildings are really complex, right? And I think also it's important for people to understand, and something that I've learned is not just about safety when the project is done, right? It's about safety of the project into the future as well. And so I'm curious, what are you working on with bamboo right now that you're really excited about? And where do you hope, round pole bamboo construction will be in 10 years, so to speak? What are you doing right now that you feel is really pushing the limits, and what are some of the outcomes you think are going to come from that?
Yeah, I think the future of bamboo in its natural form. I mean, I've mentioned a number of times about due to the nature of the shear capacity, the limitations are on the connections in the use of bamboo in certain ways. But actually, connections,
like how we join it together.
We join it together, the connection of one bamboo pole to another. But connections are being developed which will overcome the limitation on the shear capacity, which means you can connect two bamboo poles together in their length. So take two 10-meter poles, connect them together, it becomes one 20-meter pole. And effectively, because of the way the connection is, the bamboo now thinks it's 20 meters long.
So that means
mechanically it's the same. So now we can make a bamboo pole that's 200 meters long. So you could begin to think about large span structures, grid shells, surfaces that have been done in timber for a very long time can be done in bamboo. So that's enormous, right? Because it means you potentially create large scale structures with them.
And how just just so people understand, like how big are we talking here?
Oh,
When you say
hundreds of
large?
meters.
Like a span with no
Roof
columns,
spans of hundreds of meters.
hundreds of meters.
Yeah, potentially.
Yeah.
And actually,
And that would be just purely based on if we're able to increase the strength of the joinery.
the connections, because the material itself, if like I've said, we've said before, we've spoken about that actually the tensile and compression capacities of bamboo are up approaching that of steel. And far greater than timber, so the potential for it to be used in, and it's very important to understand, it is combining these ideas of the form of the surfaces with the kind of nature of the material itself, and it's that geometric stiffness that allows you potentially to. There's a very famous grid shell in Mannheim in Germany by the lightweight structures architect and engineer Frei Otto, built in the 1970s, which is a 90-meter span and made from sections of larch that are 5 centimeters. Well, the only thing stopping you doing the same thing with bamboo is the connections. And we're developing connections are being developed. We, but other people around the world, developing connections which will enable that to happen. So in terms of creating surface structures, grid shells, etc., that's a future that's very exciting. In terms of introducing bamboo in future in other ways, but people remove. Bamboo is made up of a series of very, very strong fibers, which is what give it strength. One of the forms of constructing engineered bamboo is to take the fibers themselves alone out of the bamboo and recombine them. Those fibers are very, very strong, very, very light. Currently, they're being used in the production of wind turbines, generator blades.
Yeah.
And that is because that's very, very high-tech industry, very kind of futuristic industry. And it's the fibers, like carbon fibers, that give it the strength and the kind of capacities and elasticity, which is very important in the nature of the design of wind turbines. And I mean, who would have thought that, today we'd be designing wind turbines, huge 100-meter span wind turbines from using the fibers of bamboo. And
because they're better than
because they're stronger and lighter.
Yeah.
And very recently I was introduced to a project which is a proposal for a base on Mars, which would propose taking the fibers into space as the fibers, and then you combine them with materials that they find on the surface of Mars through 3D printing, and you're able to use the fibers combined with these other materials, and that would create shell surfaces which would become the enclosures for the bases on Mars. And I've seen that as a possibility. I mean, so
well, I guess if we can build bamboo on Mars.
Well, I think the answer to the question is the sky's not the limit.
The sky is not the limit.
You can go further than the sky.
Maybe light years are the limit.
So I think I said a number of times that bamboo changed my life. I mean, it's kind of taken over my life. When I first found it, obviously I had no idea that bamboo had the potential of it. I now spend, I would say, 2/3 of my time personally, and our office 40% of its time, working on structures only from bamboo. Or bamboo in combination with other materials, hybrids of other materials, because that's another thing. The future is very exciting, is hybridizing structures. So combining steel, the biggest...
Not pure bamboo.
The construction industry I've mentioned produces 30-40% of greenhouse gases, but within a building, apart from basements, which is the biggest producer of greenhouse gases in any construction, it's the floors. So if we can replace concrete floors with timber or bamboo or hybrids of both timber and bamboo and steel, then we're beginning to look at a kind of much reduced production of greenhouse gases from the construction industry, which I think has to be, let's stop messing with it. Let's stop scraping the surface. We've got to actually do it, take it really serious and change the construction industry big time.
And you'd have a more beautiful floor too. On that note, Neil, my final, question before we wrap this up is there's probably a few young engineers out there or designers, architects interested in bamboo. And as an engineer, what advice would you give them on how to?
I came across it by accident. Because of, as I said, a friend of mine advised that I come out to meet John Hardy for other reasons, And it wasn't to come and find bamboo, but through meeting John, I found bamboo. Go find it. Go find somebody who's taking it seriously. Anybody who's interested. It is the future. I have absolutely no doubt. And as I said, our office went from doing none to doing 40% of our work. And if that doesn't suggest where it's kind of going, certainly in terms of our involvement, and I'm sure our involvement will expand. We've currently joined up with a group in Colombia. We have an office in Colombia, in Bogota, and which is because that's another center of the kind of bamboo growth and construction in South America. And it will only expand as far as I'm concerned, and we're being asked to talk to people all the time. So young engineers, young architects, if we're going to change the world, which we must, because climate change, we have to kind of pull back from the greenhouse gases we're producing. And a big way to do that is to construct with natural materials. We already have and know and understand timber. Bamboo, the potential for it is enormous, and it's not being tapped into, but it will be. And go and join that future, because I genuinely believe you'll all be. It will become, bamboo will become another material in the construction industry, alongside steel, concrete, timber, and bamboo.
So become a bamboo engineer, because we need it.
Absolutely, it's the future.
Thanks for joining us, Neil.
No, it's a pleasure. Thank you for asking me. I've really enjoyed it. Thank you very much indeed.